if this pressure P increases, Kp is independent of pressure, remember? If this fellow increases, then there's a minus raised to power minus half, so that it goes in the denominator. So alpha decreases. If you look at the reaction, what I'm saying is that if pressure increases, then reaction moves towards the backward direction. Or if the pressure decreases, the reaction moves forward. Why is that happening? Is a very simple principle which you've all learned, is the Le Chatelier's principle. And when the reaction is moving forward, if I think of just ideal gases, nothing more, then I'm creating more and more number of gases, which means I'm creating more pressure. So if I actually create more pressure, then Le Chatelier says that the reaction will go in a direction so as to oppose this. Right? So the reaction will adjust so that the pressure lowers down. That's what is happening. If I create more pressure, then the reaction moves towards the left. It creates more N2O4. If I have less pressure, then it demands more pressure. Which means it demands 2 molecules now of NO2. Right? Okay. Great. Then, to tell you about another very interesting example, which is the Haber process. Okay. Now, this fellow Fritz Haber, he discovered this process, I think, in 1906 or 1908 or something like that. Sometime around that. Huh? Somebody has got more precise dates? Yeah? What is this? Okay, now forget it. I don't think you'll be able to do it. So we'll just mark it. So, Germany used to get, so Haber was a German. So, in fact, it's such an important process that today, 1% of world's energy is dedicated to this process. So any of you chemical engineers out here, are there any in this group? No. Yeah, many. So any of you would be learning this process definitely through and through. So this is Haber who discovered the process and then Bosch who commercialized it, yeah? So, and they both got the Nobel Prizes for this. But why I'm telling you this story is because we are much far ahead of the other classes. So, yeah, Germany used to get all its, so ammonia was really required for making a lot of explosives. Yeah. And Germany used to get all its ammonia supplies from Chile. Not the chilies that you eat from. Huh? South American nation of Chile. In the form of saltpeter, NaNO2. And that was what was used for making all these derivatives of ammonia and ammonia. So whatever the explosives are, I mean a lot of explosives have nitrogen in it. Some of those PNTs, yeah. Now, during the war, Chile was with British, was under British control. So their saltpeter mines were shut down completely. This is the First World War. Huh? And then, luckily by that time, Haber had invented this process, the Haber process, where he lost 3 wives. I mean, they all divorced one by one. But then he did a lot for the humankind. Yeah, it was used in Haber's. He didn't think about the war, of course. He did it much before the war. But it was because of Haber that Germany could sustain the war for another 3 years. Otherwise, it would have been over in 1914, I guess.
So, but today it's a very, very important, and you know, ammonia is there in fertilizers, it's there in medicines, it's there in a lot of things. As I said, I mean, 1% of the world's energy, total energy, is used for just this process. So next time, the reaction is pretty simple. It's nitrogen plus hydrogen giving you ammonia, but it doesn't happen at room temperature. Although if you calculate the Kp, which we'll do next time quickly, it comes out to be 800. 800 what? Did I hear something? So Kp comes out to be 800 at room temperature, but the reaction does not take place. Any guesses why? Okay, you studied kinetics. Yeah. The kinetics doesn't allow that. Well, now that kinetics is somehow something very different. Thermodynamics gives you that yes, this will happen, but kinetics जब तक धक्का नहीं लगेगा होगा नहीं. Kinetics is not part of this, right? It's something else which we will not actually be touching upon in this course. Okay, so we'll meet again tomorrow and